In this video, we will learn all about cylinders and quadric surfaces in 3-space. Cylinders we are familiar with, but we have to extend that definition into 3 dimensions, and it may surprise you what we consider to be a cylinder. Quadric surfaces are new, but they are related to conic sections. Before we get to any of that, we need to define a tool that will be helpful in identifying and sketching all of these surfaces. So to help sketch or visualize the graph of a 3D surface, we can determine the curves of intersection of the surface with planes parallel to the coordinate planes by holding one variable constant. So essentially what that whole sentence is saying is to help us sketch or visualize, we're going to look at cross sections. And how can cross sections parallel to the XY or the YZ or the XZ plane be put back together to either sketch or identify the surface that we are working with. We call these curves traces or cross sections of the surface. So traces is the word that we're going to use more frequently in this course, but they are just cross sections. The first surface is a cylinder, so a cylinder is a surface that consists of all lines that are parallel to a given line and pass through a given plane curve. So first thing I would like you to notice is all 3 of these graphs represent cylinders in 3-space. The one in the middle, you would probably identify that as a cylinder, but less likely that the graph on the left or the graph on the right you would define as a cylinder. But in 3-space, the definition of a cylinder is basically take a plane curve. So on the left, it would be a parabola as our plane curve, right, in the XY plane. And if we extend it parallel to a given line, which in this case, parallel to the z-axis, we'd have a whole bunch of parabolic cross sections that we wind up extending, and that creates what we define as a cylinder. So on the left, we have a parabolic cylinder. And then in the middle, right, our cross sections would be ellipses. In this case, they would be circles, but speaking more generally, they would be ellipses. And we extend them parallel to the z-axis. So we have an elliptic cylinder. And the last one, our cross sections parallel to the xy plane would be hyperbolas. We extend them parallel to the z-axis. A hyperbolic cylinder. Right, so algebraically, how would we identify that we have the equation of a cylinder? So in this first one, this equation would just be y equals x squared. In 2-space, we do recognize that as a graph of a parabola. And now because there is no z variable here, z could be anything, which is why we extend those parabolas up and down along the z-axis. And that forms our cylinder part, right? So a parabolic cylinder. In the middle, these are circles, so this equation would be x squared plus y squared equals 1. Again, no z in the equation, so we have to graph x squared plus y squared equals 1 at a whole bunch of different z values. Z equals 0, z equals 1, z equals 2, z equals 3. We take all of those together, we've formed an elliptic cylinder. And then the hyperbolic cylinder here, so our intercepts are on the y-axis, not the x, so this would be y squared minus x squared equals 1. No z again, right? So any equation with only 2 variables that defines a plane curve, parabola, ellipse, hyperbola, then has to be extended, in this case, or in all 3 cases, along the z-axis, and that forms our cylinder. If this was z equals x squared, we would extend along the y-axis. If this was z equals y squared, we would extend along the x-axis, right? So the orientation of these surfaces can change as the variables that we use change. So now let's talk about traces. If we think cross sections, right, we see parabolas. If we took cross sections parallel to the xz plane, right, the other one of our other 3 coordinate planes, we would see parallel lines, right? Think about cutting the surface with a piece of paper parallel to the xz plane. Right? Think about what that would be. And then think about taking a piece of paper and cutting the surface parallel to the YZ plane. right? And you take cuts and you would see vertical lines. So how do we get those traces and make them useful for us? So use the traces of z equals x squared to sketch the graph of the surface. So just looking at the equation, we should be able to identify this as a parabolic cylinder. But we want to sketch it, so traces or cross sections will help us do that. So if x equals k, so if we're setting x to be a constant, that means our cross sections are parallel to the yz plane because we're moving along the x-axis. So let's simply think, okay, if x is -1, then z would be 1. If x was 0, z would be 0. If x was 1, z would be 1. So how do we represent these traces in a yz plane? Because there is no x. Well, it's actually a pretty nice way. So we draw z equals 0 in, and we label this as x equals 0. So now we've accounted for all three variables, our y, our z, and our x, with how we labeled the cross-section or the trace. And then z equals 1. Now that trace happens twice, when x is positive or -1. And then even though we don't have it written up, 2, 3, 4, if x was 2 or -2, z would be 4. Let me draw a better horizontal line there. And that would be x equals plus or minus 2. Right? So we're labeling each trace with the x value that created that trace. And we're putting them all, we're basically compressing all those traces into the yz plane. And the idea with sketching is we're going to try to pull them back out into 3 space. Y equals k. So in this case, there is no y value in the equation. So let's just say y equals 0. Well, then z equals x squared. Y equals 1. Well, z equals x squared then. So every trace is going to just be z equals x squared. And if y is constant, that means we are parallel to the xz coordinate plane. And every time we have the parabola z equals x squared. Right? So that's y equals k. Because every trace will look exactly like that. Every cross section will look exactly like that. And then z equals k means we're parallel to the xy plane. So if z, okay, so z can't be negative because then x squared would be -1. That's no good. So we'll start at z equals 0. And that might be important for you to note too, right? These are your notes, so maybe make a note to yourself that z can't be negative and y. But if z is 0, then that means x equals 0. If z is 1, then x would be plus or minus 1. If z were 2, x would be equal to plus or minus the square root of 2. So when z equals 0, x equals 0. So we have a vertical line, z equals 0. Then when z equals 1, we have parallel lines at 1 and -1. Right, so that's z equals 1. And then when z equals 2, so square root 2 is like 1.4. Something like that, getting closer together. And that's z equals 2. And this would also be z equals 1. This would also be z equals 2. Right, so we have a whole bunch of different cross sections or traces. And our goal is to use these to help us sketch our surface. Okay, so if we look at our surface, we have our x, our y, and our z axes. Okay, so I'm going to start with the parabolic traces. Right? If we go along the y-axis parallel to the xz, every time we have a parabola. Okay, so I'm going to start drawing some parabolas along the y-axis. I dash the back part of the line since I really don't know what the surface looks like, and I'm anticipating that part of the parabola to be on the back part of the surface. I can extend the y-axis this way. Now, there are an infinite number of parabolas. I chose to draw 3 of them. It's a sketch. It doesn't have to be perfect. And then, parallel to the xy plane, our z traces were parallel lines. And the first one was just a line where x equals 0. So x equals 0, so that would be this line, so there. And then when z equals 1, so we go up 1 on the z-axis, we have a set of parallel lines again. In the back, I'll use a dashed line. And then when z equals 2, right, we had another set of parallel lines. And we'd have a whole bunch of sets of parallel lines like that. And then moving off the YZ plane, we had horizontal lines, which we already have drawn. If we take one of the parallel lines we drew, that would create our horizontal line that we got as a trace parallel to the YZ plane. So if I take the red marker and go over just to give us a clean idea of what this surface looks like, we have a parabolic cylinder that goes along the y-axis, right? So parabolic cylinder, which is what we thought it would be. Now, will we go into this level of detail every time? No, but this is our first example using traces and understanding what a trace is. So I do think it's helpful to go through this level of detail of writing out a few traces, seeing what those traces look like, and how we can put them back together, use them as building blocks to create a sketch of our surface. Now, let's talk about quadric surfaces. So a quadric surface is the graph of a second degree equation in 3 variables. The general equation for such surfaces is ax squared plus by squared plus cz squared plus dxy plus eyz plus fxz plus gx plus hy plus iz plus j equals 0. Okay, where a, b, all the way through j are constants. Oftentimes when you see this, it's like, okay, what are we looking at? This seems like it's going to be extremely complicated. But this is the most general version of the equation. No equations, or typically no equations, are going to look this complex when they're presented to us. Oftentimes, we're going to use translation, rotation, other methods to rewrite in standard form the quadric surface as either ax squared plus by squared plus cz squared plus j equals 0, or ax squared plus by squared plus iz equals 0. Much more condensed version of that equation above. So what I want you to understand, what makes these equations different from the equations that defined our cylinders, is first we have all 3 variables present. We have an x, a y, a z, x, y, z in both versions. And on the left, all of our variables are degree 2. So x squared, y squared, z squared. On the right, 2 of our variables are of degree 2, and then z, right, that's the only variable degree 1. It doesn't have to be z. It could be x, that's degree 1. It could be y, that's degree 1. But one of the variables would be degree 1. Right? So either all 3 variables have degree 2, or one variable has degree 1, where the other 2 are degree 2. That is what defines an equation that will produce a quadric surface. Now, there are 6 kinds of quadric surfaces. The traces of quadric surfaces are conic sections, which we started to see when we were talking about our cylinders, right? Conic sections being parabolas, ellipses, hyperbolas. The key to graphing quadric surfaces is making use of traces in planes parallel to the xy, xz, and yz planes, the same way that we did for our cylinder. So our first quadric surface, defined by the equation x squared over a squared plus y squared over b squared plus z squared over c squared equals 1, is an ellipsoid, which is essentially a 3-dimensional ellipse. All traces of the surface are ellipses. And if A equals B equals C, then the equation will define a sphere. Right? So a sphere is a specific type of ellipsoid. Now, as far as traces go, I produced an example, x squared plus y squared plus z squared equals 1. So that is a sphere. That is pictured to the right. Right? We have our x-axis, our y-axis, and our z-axis. Now, as far as traces, when we're trying to talk about quadric surfaces, we're not going to go into the same level of detail as the previous example unless we have to. Typically, we want to start by thinking about k equals 0. If we can get a trace, perfect. If we need another trace, we'll keep going. And if we run into an issue, we'll also keep going and trying k equals 1 or k equals 2. Oftentimes, when we get an issue, that is trying to tell us something about the surface, an identifying feature. But let's not get too far ahead of ourselves. Let's start with the simple sphere or ellipsoid. So if x equals 0, y squared plus z squared equals 1. So radius of 1, that's x equals 0. Almost a perfect circle, just slightly off there. If y equals 0, then x squared plus z squared equals 1. Let's see if we can make a better circle this time. That's better. All right, and that's y equals 0. And then z equals 0, x squared plus y squared equals 1. All right, and that would be z equals 0. And by all means, please feel free to write it out algebraically underneath the same way that we did for that example with the parabolic cylinder. Right here, I'm just trying to move a little bit quicker, right? But go into any level of detail that makes sense for you. Our next surface, quadric surface that is, defined by the equation x squared over a squared plus y squared over b squared minus z squared over c squared equals 1, is a hyperboloid of one sheet. Notice the difference now is one of the terms is being subtracted as opposed to added in the ellipsoid. The axis of symmetry corresponds to the variable whose coefficient is negative. So in the general equation that they gave us, the axis of symmetry would be the z-axis. Now if we look at the graph we've been given, the axis of symmetry is the y, and that's related to the equation that I gave you where the y is negative. Right? So it's important to notice that there's not just one way that these equations can be written. Right? It could be negative x squared plus y squared plus z squared. It will still be a hyperboloid of one sheet, but the orientation will change based on the setup of the equation. Right? So here's our y, our x, and our z. Y-axis is the axis of symmetry. Okay. X equals 0. We have negative y squared plus z squared, which rearrange that. It's z squared minus y squared equals 1. That's going to be a hyperbola with intercepts on the z-axis. Okay, so that's when x equals 0. Y equals 0. X squared plus z squared equals 1. So that's a circle of radius 1. And that's when y equals 0. And then z equals 0. X squared minus y squared equals 1. We have a hyperbola with x-intercepts. So your knowledge of conic sections is extremely important in this video related to cylinders and quadric surfaces. If you forget how to graph a hyperbola or identify a hyperbola or a parabola or an ellipse, it's important that you go back and do a little bit of work understanding them and then coming back to this video. Right? So two hyperbolas and a circle or an ellipse, more generally speaking, we have a hyperboloid of one sheet and no issues with any of our traces. And what I'd like you to do is try to see these traces on the surface, right? You should see traces or cross sections that are circles. You should see cross sections parallel to your YZ plane, so coming forward off the page, that are hyperbolas. And then you should see traces coming off of the XY plane or below the XY plane that are also hyperbolas. Typically, the trace that's repeated, so in this case there's two hyperbolas, that will tell you that there's a hyperboloid, and then because there's no issues in this case, it's a hyperboloid of one sheet. Now there is a hyperboloid of two sheets, and that's next. The quadric surface defined by the equation x squared over a squared minus y squared over b squared minus z squared over c squared equals 1 is a hyperboloid of two sheets. The axis of symmetry corresponds to the variable whose coefficient is positive now. since two terms are being subtracted in this equation. And it's important that the constant on the right is positive before we make that distinction. If the variable on the right is negative, divide through by a negative because that might change the setup of the equation. All right, so we see our graph. There is a hyperboloid of two sheets, so there's now a space in the middle. Let's see how that translates to our traces. Okay, so when x equals 0, we have y squared minus z squared equals 1. So hyperbolas with y-intercepts, so that's x equals 0. When y equals 0, we have negative x squared minus z squared equals 1. Okay, we're going to have to do a little work here because y equals 0, negative x squared minus z squared equals 1. Well, that isn't true. There is no equation where negative x squared minus z squared equals 1 is going to produce a graph. So let's try y equals 1. That will give us negative x squared minus z squared equals 0. Right? 1 squared, subtract. So that would just be x squared plus z squared equals 0. So that's a point there. And then if y was equal to 2, then that's going to be x squared plus z squared equals 3. Right? I skipped a little bit of the algebra. You would have negative x squared minus z squared equals negative 3 and divide through by a negative. But that's going to be a circle of radius square root of 3. Right? So this was when y equals 1. This was when y equals 2. And there are no traces when y equals 0. And really, there are no traces between 0 and 1. And we also have to consider negatives. I am only considering the positives here. There would be no traces until you get to negative 1. Right? So here we only have traces when the absolute value of k is greater than or equal to 1, right, in this example. And that issue that we run into is what creates the space between the two sheets. Right? That point there, that's the vertex of the one sheet, and there'll be a vertex of the other sheet, and then we start to get our circular traces. But in between those two vertices, there are no traces. And algebraically, what it looks like is an equation that won't produce a graph. And then when z equals 0, we have negative x squared plus y squared equals 1. Changing that order, y squared minus x squared equals 1. So there we have our hyperbola when z equals 0. Okay, so there are instances where we do have to dive a little bit deeper into the traces. But again, it's trying to give us valuable information. In this case, it's telling us, hey, we have a hyperboloid. We have two traces that are hyperbolas. But we have this issue with the traces that's going to define it as a hyperboloid of two sheets. The quadric surface defined by the equation z squared over c squared equals x squared over a squared plus y squared over b squared is a cone. Right? So notice there's no constant here. There's no 1. So we're able to move and put z squared equal to the other part of the equation. The axis of symmetry corresponds to the variable that is isolated in the equation. First thing most students pick up on is the graph of a cone is not a cone in the sense that you think back to geometry. Right? Typically that would be just half of the cone. In 3 space, this graph does produce that hourglass type figure that we define as a cone. We will have a way to define only half of the cone. I'll talk about that before we leave this slide. As far as traces go, z squared equals x squared plus y squared. So when x equals 0, so this one's going to take a bit of work too, we get z squared equals y squared, which is z equals plus or minus y. Right? So we have lines as our first trace. So that's when x equals 0. They are technically considered conics. They're degenerate conics. Sometimes you don't go into that level of detail when studying conic sections. When x equals 1, we'd have z squared minus y squared equals 1, which is a hyperbola. So hyperbola there when x equals 1. Now those lines are important though because that's what defines the edges, the straight line of the cone. Y equals k, similar, right? When y equals 0, z is going to be equal to plus or minus x. And when y equals 1, z squared minus x squared equals 1. Right, so again, we have lines as our first trace when y equals 0, and then hyperbolas as our next. So y equals 1. And then when z equals 0, you'd have x squared plus y squared equals 0. So that first trace, that z equals 0, that's a point. And that's that point right in between the two halves of the cone. Z equals 1, we have a circle of radius 1. Right, and that would be z equals 1. So our traces would be circles. Again, try to identify these traces on the graph that you've been given. Do you see linear traces? Do you see hyperbolic traces? Do you see circular traces? Now, if we wanted to say only define the upper half, what we could do is take this equation and solve for z. Z would be plus or minus the square root of x squared plus y squared. The positive part of that equation would be the upper half, and the negative square root part of that equation would define the lower half. Right? So we could define the cone in the way we traditionally think of a cone, but that would require manipulating the equation just a bit. The quadric surface defined by the equation z over c equals x squared over a squared plus y squared over b squared is an elliptic paraboloid. Right? Notice that one of the variables now is only degree 1. The axis of symmetry corresponds to the variable that is isolated in the equation. So in this case, z is the degree 1 term that's isolated, so the z-axis should be our axis of symmetry. So we should expect 2 parabolic traces and 1 elliptic. So x equals 0, z equals y squared. Okay, so that's x equals 0, y equals 0, z equal, and I think I said z equals x squared here. I think I meant z equals y squared. If I didn't mess it up, well, I'm just reaffirming that. And then here we have z equals x squared when y equals 0. And then z equals 0, you have a point, right? That's z equals 0. Z equals 1, we have a circle of radius 1. All right, so that points to the vertex. Notice z can't be negative since x squared plus y squared can't be negative, so we have no part of the surface below the xy plane. Right, so k here has to be greater than or equal to 0. Right, and that's reflected in the graph of the surface. Now, again, just to reiterate that idea of orientation, if this were to be, let's say, y equals x squared plus z squared, we'd have our paraboloid, our elliptic paraboloid, going along the positive y-axis, right? So as we change variables, the orientation of the surface will change. It will still look generally the same, just the orientation. What axis serves as the axis of symmetry will be different. The last quadric surface, defined by the equation z over c equals x squared over a squared minus y squared over b squared, is a hyperbolic paraboloid. Now this is probably the weirdest looking surface, and just the axis of symmetry corresponds to the variable that is isolated again, and that's degree 1. Notice it's now subtraction between the two terms on the right. So there's our surface. Okay. Often we refer to this as a Pringle. Right? You might want to jot that in your notes because that gives a really good visualization of what that surface looks like. Most of us are familiar with Pringles. So a Pringle is in the shape of a hyperbolic paraboloid. Often a saddle, right? If you think of a horse's saddle, that would be another good example of this surface. It's probably the most difficult to sketch out of the 6. Those of you who are more artistic will probably be a bit more successful in trying to draw this. But really, we just need to be able to draw the traces in 2 dimensions to be able to identify it. Because this is a little bit more challenging to graph, if we needed an accurate graph, we would turn to some sort of graphing program. So here, x equals 0. That means z equals negative y squared. So now we have a parabola that opens down now. That's x equals 0. y equals 0, z equals x squared, so parabola that opens up. And then z equals 0, you'd have a point. Z equals 0, z equals 1, we have a hyperbola. There, so two traces that are parabolas, one trace that's a hyperbola, a hyperbolic paraboloid. So those are the 6 quadric surfaces. Now we have to just get comfortable identifying them using traces from their graphs, because these surfaces, as well as the cylinders, will be the surfaces that we build this course on top of, right? So it's really important that we get comfortable using them, identifying them, before we get into some of the calculus and other computations that we're going to look at.